What is distributed randomness? Why is it useful and how do we actually get it? My name is Philipp Schindler and I'm happy to present you our joint work on the HydRand protocol and to answer these questions. To answer the first question on what is distributed randomness, I would like to start with a simple example, me rolling a dice. While for me the result, a 4, was completely random, you cannot really be sure that this is indeed the case. I could just as likely have recorded this sequence multiple times and just showed you one of the outcomes. This already illustrates the main difference between local randomness, one uses by themselves to select, for example, cryptographic keys, and public or distributed randomness, which is used collectively. As soon as we use randomness collectively, we either have to rely on a trusted third party or some other means of checking that the randomness is indeed generated in a fair manner. Regarding collectively used randomness, Rabin introduced the notion of a randomness beacon already back in 1983. And this is already very close to what HydRand is actually doing. HydRand is a service, a distributed and standalone protocol which emits random numbers at regular intervals, say once every 10 seconds. The main difference to Rabin's original description is that HydRand, for this purpose, doesn't rely on a trusted third party. So what does random in this context actually mean? We expect a range of desirable properties from a distributed random beacon protocol. The first, and probably the most intuitive one, is unpredictability. Before a certain point in time, future random values should not be predictable. With the dice example, I already tried to illustrate public verifiability. Public verifiability holds if the participants in the random beacon protocol, or even a third-party verifier, are able to check that the random numbers are indeed produced according to the specified protocol rules. Bias resistance ensures that the adversary cannot influence the produced random numbers to its advantage. For a strong form of bias resistance, a random beacon protocol should also fulfill the guaranteed output delivery property. In this case, the adversary cannot even prevent the protocol from producing an output in each round. If we consider the example with the dice I gave before, this corresponds to me rolling the dice, looking at the result, and deciding if I want to roll again, before I show you the result. Obviously, this also biases the probability distribution of the sequence of random numbers. Liveness is a traditional property found in Byzantine fault-tolerant algorithms. This property basically ensures that the adversary cannot prevent the protocol from making progress. And of course, scalability and energy efficiency are also desirable properties we set out to achieve. Now that we know what a distributed randomness protocol actually is, let us discuss why it's interesting to look at. There is a wide range of application scenarios from different fields where random beacon protocols can be used. If we consider, for example, selection processes, it can be used for gambling and lottery services, jury selection, or even sport door events. Within blockchain and BFT protocols, distributed randomness is used for leader and committee selection, to implement sharding, as well as whenever secure random numbers are required within the deterministic execution environment of smart contracts. Additionally, there is a range of interesting use cases in online gaming, for example the fair distribution of in-game items or team and tournament assignments. Distributed randomness can also be used for generating parameters or to implement privacy-enhancing technologies in other cryptographic protocols. So now let's take a look at how we actually built the HydRand protocol. HydRand relies on a few cryptographic building blocks: digital signatures, cryptographic hash functions, and publicly verifiable secret sharing. While I assume that most of you are familiar with the first two, I will introduce PVSS shortly. PVSS is a natural extension of traditional secret sharing protocols. Here we have a dedicated party called the dealer which wishes to share a secret, denoted by S, among a set of parties. Any subset of at least 3 parties in this example should be able to compute the shared value. Any fewer than 3 should not be able to learn any information about the secret S. The main difference between PVSS and secret sharing is that we have to trust the dealer in the secret sharing setting. A publicly verifiable protocol, on the other hand, enables all parties to detect a malicious dealer at the time the shares are distributed. For this purpose, efficient non-interactive zero-knowledge proofs are used. With the cryptographic building blocks sorted out, let's have a look at HydRand's system and threat model. We assume a fixed set of known participants. Less than a third of those may behave Byzantine, which means that they may arbitrarily deviate from the protocol. The threshold used for the internal secret sharing protocol is set to just over a third. This ensures that the adversary on its own can never compute a shared secret. Regarding the network model, we assume a synchronous network with a known upper bound on the network propagation delay. Digital signatures are used to implement authenticated point-to-point messaging channels. Apart from that, we do not make any additional assumptions in regard to, for example, a distributed key generation protocol or a common broadcast channel. Now we are ready to have a first look on how HydRand actually works. During the setup of the protocol, all participants exchange public keys and initial PVSS shares. This means that every party shares one randomly picked secret with all other parties. To complete the setup, all parties agree on an initial random beacon value and start the protocol. The execution of the protocol is split into consecutive rounds. Each round is separated into 3 phases: the propose, the acknowledge, and the voting phase. At the end of each round, a new random beacon value is produced as output. This value is also used to select a new leader for the next round. And now we will have a more detailed look at the 3 protocol phases. In the propose phase, the leader broadcasts a signed message to all other nodes. This message contains 2 main parts. First, the leader reveals the secret he previously shared, either during the setup phase or the last time he was selected as leader. Second, he includes shares for a new randomly picked secret in encrypted form in his message. During the acknowledge phase, each node which previously received a valid message from the leader broadcasts a signed acknowledge message. This message forwards the received secret as well as includes the hash and signature of the received proposal. On the one hand, including the hash ensures that the malicious node which sends out different messages during the propose phase is later detected. On the other hand, sending the leader's signature prevents a malicious node from wrongly accusing a correct leader. During the vote phase, each node again broadcasts a single signed message, either a confirm vote or a recovery vote. A node votes confirm if it received 2 F+1 acknowledge messages for the leader's proposal. Otherwise, it sends out a recovery vote. This recovery vote includes the node's share for the leader's secret in decrypted form and may later be used to recover the leader's shared secret. With the voting phase completed, we can finally compute the random beacon protocol output for this round. There are basically 2 options. The one depicted on the left side, where we have received 2 F+1 confirm votes and the corresponding acknowledge messages, and therefore already know the revealed secret from the leader. On the other hand, on the right hand side, we have received F+1 recover votes. These votes include the shares for the revealed secret in decrypted form, and these shares can be used to again compute the recovered secret. And no matter which of the both ways we compute the shared secret, they actually are equal. This is guaranteed by the properties of the PVSS protocol used. To finally derive the new random beacon output for this round, all we have to do is combine the revealed or recovered secret from this round with the previous output of the protocol, using a cryptographic hash function. The last step required to finish the round is to select a leader for the next round. This process does not require any interaction. Instead, we use the random beacon output we just computed to uniformly at random pick a new leader from the set of potential leaders. A node is considered a potential leader if it was not selected as leader during the last F rounds. Additionally, we exclude all nodes which previously failed to fulfill their duties as leader from the set of potential leaders. This, for example, excludes all adversarial nodes which try to stall the protocol by withholding a secret which they should have revealed when they are leader. To further demonstrate how the HydRand protocol handles different situations, I would like to walk you through an illustrative execution run. In round 1, the adversarial node 4 was selected as leader, and the adversary tries to attack the protocol by by only selectively sending information to the honest nodes 1, 2, and 3. Therefore, the honest nodes which didn't receive any messages don't acknowledge the leader's proposal and vote for a recovery. However, the first 3 honest nodes nevertheless gather the required number of 2f+1 acknowledge messages and vote for confirm. Even though the views of the correct nodes are temporarily different, they produce the same random beacon output. The views automatically converge as soon as an honest node is selected as leader again. This happens after at most f+1 rounds. In the next round, an adversarial or failed leader doesn't send any messages. Consequently, no acknowledge messages are sent out. All correct nodes vote for recovery and reconstruct the round secret using the PVSS shares. In round 3, the third honest node is selected as leader. It broadcasts a new proposal to all nodes. This proposal refers to the proposal received in round 1. It is valid and hence acknowledged and confirmed by all nodes. If instead node 6 or node 7 would have been leader in this round, they would not refer to the proposal from round 1. This is because those nodes have also received f+1 recover votes for round 1. In the last round, in this example, we have again the adversarial node 4 as a leader. This is possible since the previous leader resolved the disparity from round 1 in the adversary's favor. If the previous leader was node 6 or node 7 instead, the adversary 4 could not become leader in this round, because in their view node 4 didn't send a valid proposal in round 1. To continue with the example, the adversarial leader of round 4 does not send out his proposal to the honest nodes. The acknowledge messages he sends out don't influence the correct node's decisions to vote for recovery in this round. The leader's secret can successfully be recovered. Intuitively, this is the case because nodes 1, 2, and 3 have received the leader's previous proposal and thus know f+1 shares required for the recovery. Notice that the recovery succeeds even though the honest nodes 6 and 7 never received their PVSS shares. With this understanding of the HydRand protocol, let's revisit the desired properties we set out to achieve in the first place. The first property, unpredictability, is guaranteed after f+1 rounds. Intuitively, this is the case because the way we select leaders ensures that within f+1 rounds there is at least one honest leader. This leader acts as a barrier for unpredictability, as the adversary doesn't know the honest leader's secret and isn't able to compute it using its PVSS shares. However, probabilistic unpredictability is already guaranteed after a few rounds, because in each round a correct leader is selected with a probability of about 2/3. For all nodes running the HydRand protocol, public verifiability is immediately guaranteed. However, also external verifiers can easily check a produced protocol output for a particular round using the leader's proposal and 2f+1 confirm messages for a corresponding round. In our paper we proved that HydRand also achieves bias resistance and guaranteed output delivery. This is the case because no action the adversary takes during any of the 3 protocol phases can influence the produced output. The adversary can also not prevent an output by withholding information. In this case, other nodes can always recover missing values. Similarly, we also show that the traditional liveness property holds. To demonstrate HydRand's scalability in practice, we implemented the prototype in Python. This prototype is used for extensively benchmarking our solution. We tested different scenarios with up to 128 globally distributed nodes. These nodes were spread equally over multiple data centers in 8 AVS regions. Even in the most demanding scenario, with 128 nodes and simulated adversaries, HydRand is able to reliably produce random numbers in intervals of less than 10 seconds. In this scenario, verification of the produced randomness takes approximately 50 milliseconds, and the corresponding proofs are a few kilobytes in size. The required network bandwidth is quite low, and the performance of the protocol was most likely CPU limited, as we used EC2 microinstances, which only have 1 GB of RAM and 1 CPU core available. HydRand is also energy efficient. In no point of the protocol are any expensive cryptographic primitives, for example, mining algorithms as found in Bitcoin, used. Now, with the HydRand design fully covered, let's take a quick look on some future protocol improvements. Regarding scalability, one could use threshold cryptography, for example BLS signatures, to reduce the size of the messages being sent. Similarly, one could use pre-shared secrets or distribute the PVSS shares in parallel to the protocol execution. This minimized bursts during the message transmission. If a node temporarily fails, it is excluded from the further protocol execution in the current version of the protocol. However, for a long-running protocol instance, it might be desirable to allow such parties to rejoin. To rejoin, an excluded node publishes new PVSS shares. It can be selected as a leader as soon as the remaining nodes agree on the rejoin request. That happens after at most f+1 rounds. Furthermore, one could modify HydRand to consider a different model, for example by reducing the reliance on the network synchrony. However, it is not clear how the strong form of guaranteed output delivery can be achieved in this setting. Alternatively, one could try to stay in the synchronous network model while tolerating up to a 49% adversary. Lastly, I also want to point you to our paper, where you can find a detailed comparison of HydRand and other protocol designs in this field. Unfortunately, in this short talk, there is not enough time to cover them all. If you have any questions in this regard, or on HydRand's design itself, I'm happy to answer those questions right after the talk or during the breakout sessions. And with that, I would like to conclude this talk with a quote from Donald Knuth. Random numbers should not be generated by a method chosen at random.